Okay, welcome to the review of the summer material here. I'm going to try to do my best here to go over all of these questions, and if you have further questions about my explanations, either email me or come and see me if school's in session. Okay, so we have a density and we have a mass, and it looks like we're trying to solve for volume. So density equals mass divided by volume, or volume equals mass divided by density. What else do we have here? We have all of our answers in liters. So 1,000 milliliters equals 1 liter. And by the way, also in our density, centimeters cubed is given. 1 centimeter cubed equals 1 milliliter. So we're going to have to do a conversion by the time we get to an answer here. So what do we have for mass? We have 500 grams. And then we also have a density of 2.50 grams for grams per centimeter cubed. So when you do that math, that's going to come out to be 200 milliliters. Well, we need to convert this to liters. So if we divide that by 1,000, we'll get answer A. So this was about a density equals mass divided by volume question and about a conversion of units. So in first year chem, you would have just a density question, or you would have just a conversion question. But in AP chemistry, we'll use a lot of the same concepts you learned last year, but we might combine them, 2 of those or 3 of those, into one question. Number 2, we have a graduated cylinder that contains 50 milliliters of water, and then you put a piece of gold in there and the volume increases. So if you want to know the volume of the gold, you'd have to subtract those 2 numbers. So 77.0 minus 50.0 would give us the volume. But we want to get a density. So we're using the same equation we used above. Density equals mass divided by volume. So there's going to be our volume on the bottom, but we need a mass, and we were given a mass of 521 grams. So when you do that math, I think that comes out to be 19.3 grams per milliliter. Okay? So again, we had to do a subtraction for volume, and we had to do a density equals mass divided by volume question. Number 3, no math on this question. Student wants to measure out exactly 60.0 milliliters. So that is 1 decimal place. So beakers are not going to be acceptable. Beakers are terrific at holding liquid chemicals. They're good for mixing solutions. They're good for heating solutions, but they're not good for measuring because they don't have enough increments. 10 milliliter graduated cylinder isn't going to get us to 60, so we'd have to use that 6 times, and that's not really what going to give us the most accurate results. Volumetric flask measures exactly the volume that is designated. In this case, 100 milliliters would measure exactly 100 milliliter solution or sample. So the most increments, meaning the most precision, is going to be 100 milliliter graduated cylinder. And that, at least the ones we have, would always measure to 1 decimal place. If you need more than 1 decimal place, you can also use a burette. You may have used those at the end of the year in acid-base titrations. And we also have some pipettes that have a lot of increments on them, and we'll occasionally use those too. Number 4, Correct sig figs is about what this question is trying to ask. And we have answers of 4 sig figs, 3 sig figs. The 0 is not significant, but the 9, 6, and 6 are. So this one also has 3 sig figs, and this one has 2 sig figs. So we might be able to get away with not having to do math, just looking at the significant figures that are in the measurements. So 22 milliliters has 2 significant figures, and this has 5 significant figures. So 5 significant figures for our mass divided by 2 sig figs for our volume. When you do multiplication division, the answer should have the least number of sig figs in the measurements. So we need an answer that has 2 significant figures. And if I don't have to do the math, I would save myself a little bit of time, and I know that it's going to be the only answer that has 2 sig figs. Now, if there was 2 answers there that had 2 sig figs, we'd have to do the math. Number 5, percent error. Percent error is experimental minus true divided by true times 100 to get it into percentile. So what do we got here? We have student measures that, and the true is that. So instead of me rewriting this again, I'll just pop this into their 2 spots. So 2.850 minus 2.699. Make sure that you do that function on your calculator first, and then divide by the true density of 2.699. And when you get that answer, that should be 5.59, not with your calculator, but rounded to the correct number of sig figs. Why do I use those numbers as sig figs? So when I do the 2.850 minus the 2.699, that subtraction, I have to go to the right number of decimal places. So that gives me 3 decimal places. So that's going to give me a 0 point with 3 decimal places. That is 3 sig figs. And then I'm going to divide that by the true value, which has 4 sig figs. So now 3 sig figs divided by 4 sig figs gives us an answer of 3 significant figures. And I had already calculated it was 5.59. So again, subtraction and addition, it's the least number of decimal places. And then multiplication division, it's the least number of significant figures. Okay, percent composition, empirical formulas, and molecular formulas. We have amounts of 3 different compounds. If these weren't in moles, we would have to convert them to moles. And the trick with this one is you convert them to moles first, which they're already in moles. Then you divide them all by the smallest amount, and hopefully those are all whole numbers. If they're not whole numbers, you multiply until you get whole numbers, or very, very close to whole numbers. So 0.50 moles of K, and we have 0.25 moles of, whoops, that looks like iron. I don't want that to be iron. And then 0.75 moles, and it looks like our smallest amount is 0.25. So I'm going to divide them all by 0.25. And when I do that, I'll get 2 Ks. I'll get 1 TEs, and I'll get 3 oxygens. And so do we have one that matches up with that? Looks like we do. Okay. Again, if these did not come out to be whole numbers, the 2, 1, and the 3, we would multiply them. Like say it came out to be, one of these came out to be 2.25. Then we'd have to multiply everything by 4 to get them in a whole, to get them all whole numbers. If it was 2.33, if we multiplied everything by 3, that would get them into whole numbers, and that kind of go with that idea there. Okay, next one. Highest percentage of oxygen by mass. So that means it has to have the most oxygen compared to the rest of the molecule. So, so you'd want oxygen to have a lot of mass and the rest of the compound to have relatively low mass. So if I look at A, oxygen weighs 16 for H2O, but 2 H's and 1 O weigh 18 grams. So if you would divide those two and times 100, you would actually get the percentile, percent oxygen in the compound, and no other compound B, C, or D is going to give you anything close to that. Let's see here. Number 8. 16 grams of hydrogen. How many grams of methane are required to get there? So I think this is a little bit of a factor label question. So 16 grams of hydrogen were given. And I just divide that by 1 so I can tell that am I going to be multiplying or dividing 16, so I don't lose track of what I'm doing there. And I'm going to convert that to moles. And on the periodic table, it's about 1 gram. If we're doing a multiple choice question, there's only 4 answers. I'll just use 1 gram instead of using all the decimal places that are on the periodic table for hydrogen or any other atom. And that would give us 1 mole of hydrogen. And then I'm going to convert that from moles of hydrogen to moles of CH4. So there are 4 moles of hydrogen in 1 mole of CH4. And then moles would be terrific, but we need to get it in grams because all the answers are in grams. So in 1 mole of CH4, I'd go on the periodic table, and that weighs approximately 16 grams of CH4. So it looks like we got 16 divided by 4. I'm trying to do this in my head instead of using a calculator. I think that's 4. And then 4 times 16, I think that's going to give us an answer of 64 grams. Number 9 is a thinking question. So element Q, an unknown element, we're not really sure what it is. We have 1 mole of 4 different compounds. They all have different masses, 38, 57, 76, and 114. What could be a possible atomic weight of Q? Well, all those compounds have Q in it. So all 4 of those compounds better have a similar divisible number because they all have to have the atomic mass of Q. So if I look at all those 4, can't really put my number under 114 there, but if I divide them all by 19, it's hard to put that one in there, but if you divide them all by 19, you better get a whole number if the compound has an element that has a mass of 19. If you try this with the other 3, 12.7, 38.0, or 57.0, you're not going to get a whole number. So that means it's not divisible and it can't have those different masses. So that's why I like answer B. Can you find that in any page of a textbook? No. So you have to use your ideas of atomic masses, of the mole, and you have to be able to think through the question. So this one's definitely a AP style question. Material, first year chem, but it's definitely complexity of AP Chem for that one. Number 10, we have a percentile, and we're trying to get the simplest formula, which is called the empirical. So that's the simplest whole number ratio between nitrogen and it said of an oxide. So that means it has to have oxygen too. So it has to have N and it has to have O. And I put X and Y there because we don't know what those numbers are. So if I had 100 grams of the whole compound, 36.8 grams would be nitrogen. The rest of the 100 grams would be oxygen. So 100 minus 36.8 is 63.2 grams of oxygen. And we're going to convert grams to moles. There's 14 grams of nitrogen and a mole of nitrogen. And then for oxygen, it's 16 grams. So that's going to give us 2.63 of nitrogen. And we're going to have 3.95 moles of oxygen. Neither of those are whole numbers. So if we divide them both by the smallest, we get 1 nitrogen, and we get 1.5, of oxygen. Those aren't whole numbers, but if we multiply them both by 2, we get 3 and 2. And we do have an answer that has what we're looking for. Number 11. A hydrate is a chemical composed of a salt and water that's loosely attached. And it looks like all 4 of these answers have 3 waters, 5 waters, 7 waters, 10 waters. I'm looking at D, C, B, A. It says it loses 54.3% of its mass. So when you heat it, it loses 54.3% water. So therefore, we know how much water it has. We're trying to get this empirical formula here that has some Na2CO3 and then different amounts of water. So again, we want an answer that has 54.3. So this is pretty much, you might have to guess and check. Do A, do B, do C, do D. I'll jump to the correct answer, B, but I think you're going to have to do all 4 of these. So we want to get a percentile, we want to get this to happen. The part we're interested in, which is water. So for B, it's 7 waters, and water weighs about 18 grams. So that's our part. And then our total would be 2 NAs, because there's Na2, 1 C, 3 O's, and the 7 waters. So the rest of the molecule, Na2CO3, weighs 106 grams per mole. And then we're going to add that to the water mass. And then to get into percentile, it's a times 100. So when I do that math, 7 times 18, and then the bottom, and divide those 2 terms, I will get 54.3%. The rest of these answers, A, C, and D, won't come out to be that. Could you do some of that in your head? You might be able to, but I think at the point you guys are at in the beginning of the year, you might have to do all 4 of those to get to the answer 54.3, or at least some part of it. Number 12. We need to get that ratio of chromium to oxygen. So I think this might also be a guess and check for you guys. Again, we want to get to a 1.62 to 1 ratio. And I did guess and check all 4 of these, and I got to answer B. And how did I get that? Chromium has a mass of 52 grams. Oxygen has a mass of 16 grams. So if I like CrO2, that would be 52 grams of chromium for every 16 plus 16 because it's CrO2. So 52 to 32. So that's hard to maybe see that that's a 1.62 to 1 ratio unless we divide them by 32. And if we do that, we get 1.62 to 1. But I think you guys might have to, again, do that as a guess and check. Okay, 13. Empirical formula, again, is the lowest whole number ratio. So we need to take all those percentiles and we need to convert them into moles. I'm not going to have enough room to put the oxygen, so I'm going to move it way over here. 53.3 grams of oxygen. Okay, so 1 mole weighs 16 grams for oxygen. 1 mole weighs 12 grams for carbon. Now again, if I was interested in something where I needed a lot of decimal places, I would go on the periodic table and find all the decimal places that go after 12, or I think for oxygen it's going to be 15 point, really close to 16, but they're not exactly whole numbers. But in this case, empirical formula, we're not going to have to worry about that. Okay, for hydrogen, it is 1 gram. So let's get some answers here. We have 3.33 moles of carbon, 6.71 moles of hydrogen, and we have 3.33 moles of oxygen. So those aren't whole numbers, but if we divide them all by the smallest, which is 3.33, we get 1. We get about 2. And we get 1. So the empirical formula would have to have 1 carbon, 2 hydrogens, and 1 oxygen. And so the answer doesn't get lost. I would box those answers so that it's easy for anyone that's grading that to find it. Determine the molecular formula. The molecular formula has to have that ratio of 1 carbon to 2 hydrogens to 1 oxygen. But it also has to have this molar mass. So to figure out the molecular formula, if you take the molar mass and divide it by the empirical mass, so I'm going to add up 1 carbon, 2 hydrogens, and 1 oxygen. And when I do that, that weighs about 30 grams. And when I divide those two numbers, that gets me really, really close to 3, which means that I need to multiply the empirical formula by 3. So 3 times 1 is 3, 3 times 2 is 6, and 3 times 1 is 3. Let me make that 3 a little better there. Okay. 14. Molar mass. I think you guys are, or you should be pretty good at calculating molar masses. You have to go in the periodic table, and find 1 Be, 2 carbons, 4 oxygens, and then 3 waters, which would be 3 times 2, 6 hydrogens, and 3 times 1, 3 oxygens. I had done this in my head. I would probably prefer to see a few decimal places, but for purposes of being able to do B and C, if we have a molar mass of 151, that's going to be fine. Okay, calculate the mass percent of carbon. If you want to do any percentile, it's the part that you're interested in divided by the total times 100. So in this case, we're interested in carbon. So if I look at how many carbons are in this molecule, it's 2. So 2 times 12 is 24 grams. So I have 24 grams of carbon, and then I have to divide that by the entire molar mass, which I had just done, which was 151. And then again, percentile means multiplying it by 100, and I get 15.9% carbon. Okay. Part C, we hydrate. The hydrate has been heated, so it's going to lose all of its water. 3.21 grams of the hydrate is heated. Calculate the mass of the anhydrous. The anhydrous is after it loses all of its water. Okay, so the only piece of information we have to go on is the hydrate. And we had already figured out that the hydrate weighs 151 grams per mole. So now I got moles of hydrate. And we're interested in water. So why don't I try to convert this to water? So in 1 mole of the hydrate, I have 3 moles of water, but I really don't want moles. I have been requested to get grams. So in 1 mole of water, there's 18 grams of water. So that comes out to be 1.15 grams of H2O that is released. So that's only half of the question. That was the mass of water released, but it doesn't tell me the mass of the anhydrous. But I had 3.21 grams of the hydrate, and I lost 1.51 grams of water. So whatever's left should be the anhydrous, which is 2.06 grams of the anhydrous. So that was definitely, you might think of it as stoichiometry. We haven't really got the stoichiometry yet, but that's definitely the chapter that you had the mole in. Okay, so let's see what we got here. We have 2 isotopes. So I'll show you how to do the math, but you might be able to arrive at this answer without doing the math. So 1 isotope weighs 63 AMUs, it's called atomic mass units. And I was guessing and checking. If I was going to do the math, I would guess and check. And I'm going to go to this answer 25 because that is the answer. That means that 25% is the isotope 65. That would mean that 75%, let me change this to percentiles. So 75% would be the 63 isotope, And that means that the other isotope, 65, is the 25%, or 25 divided by 100. And if you do that math, that's going to get you really, really close to the atomic mass, average atomic mass of copper. But without math, let's look at this. So the average is 63.55. It's made up of two isotopes, 63 and 65. If it was 50-50, between 63 and 65, that would give you a mass of 64. Well, we don't have 64. We have less than that. So that's why I know it can't be that. I also know that's why it can't be that. It has to be less than 50%. And so that took me down to C and D. You might be able to do also that without doing any math, but if you're not comfortable with that, you could do the math of those two, and you would still arrive at the right answer, answer C. 16, not correct. So we have a mass of 23 and atomic number of 11. So mass, by the way, that mass of 23 is the protons and the neutrons. The atomic number 11 is the number of protons, and it's also the number of electrons. So we just have to figure out which one doesn't match up with that. And it's going to be B. So let's talk about some of these answers. Most of them, let's see, its atomic number, its number of protons is 11. So we knew that was a correct statement. Number of protons is 12. Well, if we know that there's 11 protons, we'd have to have 12 neutrons to get a atomic mass of 23. So we know that's right. And then always the mass is concentrated in the nucleus. Outside the nucleus, we have the electrons, and they are relatively, they have very little mass. 8 electrons in its outermost shell. Well, if it has 11 electrons, it has 2 in its first energy level, it has 8 in its second energy level, and it has 1 in its third energy level. So it goes, again, the 1s, if you remember that can hold 2 electrons. The second energy level can be 2 plus 6 is 8. And then I'm running out of room here, so I'll put it down there. And so now the third energy level has 1 electron. Okay, number 17. Very similar question. Which of these are going to be isotopes of each other? So isotopes have to have the same atomic number. And it looks like the only one that has the same atomic number is this. So we're not going to bother looking at A, B, and C. 18. So I think you're going to need a periodic table in front of you for this one. You have these two elements. If I look at the periodic table, I get that mass, and I get that mass. Now these are the averages of all their isotopes. A sample that is believed to be a mixture of I and Te run through a mass spectrometer. By the way, that's the machine that is able to identify percentages of different isotopes. And we have this data below. Which one would be the best basis for concluding that the sample was pure Te? So again, these two numbers that I threw out here are averages from the periodic table. of all the isotopes of those two. This one here deals with charges. Charges have nothing to do with the information provided. Abundance in the universe, this graph has nothing to do with that information. Iodine consists of only one naturally occurring isotope with 74 neutrons, whereas Te has more than one isotope. Well, we definitely have a whole bunch of isotopes here. Every one of these peaks is an isotope. So that's a possibility. We'll come back to that if we need it, if we need to come back to that. And then we have D. Iodine has a higher first ionization energy than Te. There's nothing in this question that deals anything with ionization energy. So without a tremendous amount of information to go on here, and we can go process elimination, that all three of those answers have nothing to do with the question at all. Okay, now we have some stoichiometry here. So to do stoichiometry, we're going to need to have balanced chemical equations if it's a chemical reaction. Number 19. We have some chemicals that are going to react. The chemical reaction is a 1-to-1 reaction. I would normally write the ones, but NaCl, and H2O. So we need equal amounts of both of those chemicals. So volume and molarity, we can get moles. Volume and molarity, we can get moles. And we have to compare moles to do this question. So 2 molar means 2 moles in 1 liter. I wrote 1,000 milliliters because that's the same thing. And we were given 100 milliliters. So that's going to give us 0.2. Let me rewrite that. Moles of sodium hydroxide. Doing the same work for the hydrochloric acid, 1 molar and 300 milliliters. That's going to give us 0.3 moles of HCl. So we have 0.2 and 0.3, but it's a 1-to-1 ratio between those two chemicals. That means the sodium hydroxide is going to be the limiting reactant, and that means that the acid is going to be excess. So we're going to have a limiting reactant and an excess reactant. So after the reaction's complete, there will be acid in the beaker. So we would have to pick the answer that deals with that there's acid in the beaker. 20. We have the formation of water from hydrogen and oxygen gases. And we need to balance this. Okay? So we need to look at these 4 answers. On the left-hand side is before the reaction occurs, and on the right-hand side is after the reaction occurs. That and that are off the board immediately. Why? Because H2 is a diatomic, 2 atoms in the molecule, and oxygen is diatomic, 2 atoms in the molecule. So those are off the board. I kind of like C here, and let's talk about C. So did you notice there these atoms that are in the molecules here are not the same sizes. Hydrogen is very small, oxygen is very large. So we have 1, 2, 3 oxygens. I'm going to write it down there. I'm going to do something called ICF. Initial, what we have initially, what kind of changes might occur, and what's in there finally. We have 1, 2, 3, 4, 5, 6 of the hydrogens. And then over on the products, we have 1, 2, 3, 4, 5, 6 of the waters. But we didn't have any waters before we do the reaction. Where we have the waters is final. We ended, this column here is the final, and this column here is the initial. How they get from one side to the other is the change. So 0 plus something gives us 6. So I think that's going to have to be 6. These ratios are the changes. So if there's a 6 here and it's a ratio of 2 to 1 to 2, we would have to have the same numbers where the 2's are the same. And I just wrote a 6 here. Hydrogen is 6. We have to lose reactants. 6 minus 6 is 0. So did you notice in this beaker, whatever it is here, this container, there is no hydrogen left. It's a 2 and a 1, or a 1 and a 2 for oxygen, hydrogen, and H2O. So if we have a 6 for there, we would need to have half of that over here. Half of 6 is 3. 3 minus 3, 0. So we have also none of the oxygen gas in the final. So that's why I liked answer C. 21. We have a reaction, and it's already balanced. I'm going to write the I, the C, and the F just like I did before. It said we have equal moles. So we can make these numbers whatever we want. 100, 622. I think the easiest numbers to use would be 2. So it says we have equal amounts of potassium and chlorine gas, and you never have any products before you start. We're going to have some changes. We're going to lose some reactants, and we're going to gain some products. And the question is really not about the products too much. It's because KCl is in all 4 of the answers. But it wants to know what's going to be what remains after the reaction is complete. So that's going to be this column right here. If we have any numbers, that's that answer. So it's a 2 to 1 to 2. I'm going to erase those numbers, but that means that 2 potassiums have to be used up for every 1 chlorine. So if I would go like this, 2 minus 2 would be 0. If I used up 2 potassiums, I better use up half, because it's a 2 and a 1. So that would mean I would have to use up 1. 2 minus 1 is 1. We don't really care too much about the products because all 4 of these answers have KCl in it. But it's a 2 to 2. So if I have a 2 for a change there, I would have to have a 2 for a change there. 0 plus 2 is 2. So what's in the beaker when we're all done? We had Cl2 left over, and we made KCl, which looks like that's answer C. So we're going to start to see a theme here with these questions with stoichiometry. Number 22. So I'm going to have to write this reaction here. Whoops. So that's going to make, it's a double replacement precipitate reaction. It's going to make some sodium nitrate, and it's going to make some silver phosphate. Initial, change, final. So this wants us to rank what's in the beaker when we're done. This chemical here is soluble, ionic, so it'll produce ions. This, same thing. This, same thing. This column here, we're not going to be interested with this question because it is a precipitate, solid. So it won't give us any ions. Okay, what do we got in the beaker? We have 100 milliliters of 1 molar and 100 milliliters of 1 molar. So we have identical amounts of chemical. It literally doesn't matter what numbers you put there, but we'll put the correct numbers, which would be let's make this 0.1 moles of sodium phosphate and 0.1 moles of silver nitrate. And remember, you never have any products before you make them. We're going to lose some reactants and we're going to gain some products. Remember, this last column, the silver phosphate column, is a solid precipitate, so it won't give us any ions. This isn't balanced, and if we don't balance this, we're not going to be able to answer this question. Okay, so now it's a 1-to-3 ratio. So I think this is going to be our limiting reactant. And if it's a 1-to-3 ratio, where I have a 0.1, I better have a third of that, which is about that. It doesn't matter specifically that I have numbers in there because none of these 4 answers have numbers, but that's going to give us about somewhere in that range. And then it's a 3 and a 3. So whatever number we have for change for silver nitrate, we'd better have the same amount for sodium nitrate. Okay. Now those are moles, but they're all in the same container. So the volume is not going to impact making these moles a different ratio from each other. Okay, so let's try to get to some answers here. Well, we have no silver nitrate left, and we didn't make any silver phosphate ions because it's a precipitate. So silver ions would be virtually 0. Oh, none of the 4 answers have silver in it, so that's not going to help us out. Let's use the same idea, but in the opposite way. Which one would have the most ions? So we have sodium phosphate, sodium and phosphate left over, and we made sodium nitrate. What did I say that was left over and made? The sodium ions. So I think the sodium ions are going to be the highest concentration. So now we're down to answers A and C. Okay, so what else do we have here? We have phosphate left over, 0.066, and we made sodium nitrate, 0.1 moles of sodium ions, 0.1 moles of nitrate ions, and 0.1 is more than 0.066. So I think there's more nitrate than there is phosphate. So I think that's the most labor-intensive question for the multiple choice, but very good question for AP Chemistry. 23. Again, stoichiometry. ICF. Initial, change, final. So we have 8 grams and 92 grams. Well, grams we can't put in these to compare in anything any stoichiometric calculations. We need to look at moles. So 8 grams, I'll write it up here. I'll do one of these. So we have to get these into moles. So 8 divided by 32 is 0.25 moles. I don't have enough room to put the moles in. And then 92 grams, and the molar mass is 92 grams per mole. So that means we have 1 mole of that. Remember that we don't have any products before we start. And it looks like we're only interested in the H2O. So we're only really interested in one of these two columns. So I'm not even going to be bothering with, well, I'll leave it in there, but I really don't care what happens with the N2. But we will make some N2 and we will make some water. We will lose N2O4 and we will lose N2H4. So I think we have a lot less of the N2H4. So we're going to have to lose it all. Something's always going to be the limit reactant. And it's a 2 to 1. So this number here has to be that same ratio, 2 to 1. So 0.25, half of that is 0.125. I don't really care about the N2, so I'm going to skip it. I care about the H2O, sorry. And it's a 2 to 4 ratio. So I have to double this number for that spot. So double 0.25 is 0.50. So 0 plus 0.50. Okay, that'd be great answer, except I need grams. So to get that into grams, 18 grams of water in 1 mole. So 0.5 times 18 is 9. Same style question again. Instead of rewriting the equation again, I'm just going to put my ICF underneath of A and 4B and C and 4D. So we have 6 moles of A and 20 moles of B. And again, for the products, we don't have any products. We're going to lose reactants. We're going to gain products. And this time it only asks for D. So we're only interested in this last column. So we have to figure out what the limit reactant is. So let's guess that's this one. 20 minus 20 is 0. One of these two reactants have to come out to be 0. So I think it's the B. It's this one that's going to be the limit reactant. Okay, now it's a 4 to 1 ratio. So if I put 20 in for B, I have to put 1/4 of that for A. And 1/4 of 20 is 5. 6 minus 5 is 1. And again, we're only interested in what's going on with the D. So I'm just going to worry about that. So it's a 4 to 4 ratio. So if I put 20 for B, I better put 20 for D. So 0 plus 20 is 20. Okay. 25. This is very tricky too. Definitely AP style. So we have some Xe and F2 gases. Initial moles. Whoops. F2 was 8 and Xe was 1.7. When all of the Xe has reacted, so that means all of it reacts, well then that means that we'd have to put that number in for the change for Xe. How much F2 do we have left over? We have 4.6. Well then, how much would we have had to react? 8 minus something gives us 4.6. I think that's going to have to be 3.4. This doesn't really matter because we're not being asked about what's going on with the initial change or final for the product. But what we're trying to find out is what goes into these spots. So those spots always have to match up. These have to match up with the change. So a 1.7 to 3.4 ratio is the same as a 1 to 2 ratio, a 1 to 2 ratio. So 1 Xe and 4 Fs. There we go. And I think we're going to conclude there for those questions. I'm going to do part 2 for the net ionics.